So let's go ahead and get started and at least start warming up, so we'll give stragglers another minute or two to show up. Well, let's take 5 minutes or so and attempt these kind of warm-up problems here. And some of you may already be working on them. That's great. Bug your partner, bug your neighbor. Ask me if you need a little jolt to get going. But definitely get help, ask questions. I want to go over this and make sure we're really solid on conversion factors and converting, since this will only continue to carry over. And then as you kind of sit there, work through this and process lecture. So I handed out this little yellow paper, and I think some of your other classes are trying this, so I wanted to try this in here. And it's called like the muddiest point. And so I want you to think back on like this first week, and what's the muddiest point that occurred in lecture? What needs clarification? And that way I know kind of what to hit again, maybe next week, and see where people are struggling. And so I just want to see how we're doing. And so just turn them in wherever as you leave class. And then put your name on it. So again, that's just, you can think about that as you do these warm-up problems. All right, let's start going over these. And so tell me what you did. So we have 7 meters starting off. And then what do we pick for our conversion factor here? 100 centimeters over 1 meter. So that looks excellent. So there's our conversion factor that hopefully you have written out on this chart in some form. And then again, good job in picking that the centimeters needs to go on top. That's the unit that we want. Meters is going to cancel. And then what's our final answer for this one? So 700 centimeters. All right, let's do this next one. So 60 milligrams to kilograms. So somebody tell me, how do we do this one?
I was a little bit confused. I feel like there might be 2 steps.
Yeah, so that's good. So you kind of remember, where was our 2-step from last time? I can't remember where I put the example. Oh. Sorry, I don't know why I can't find yesterday's example of our 2-step conversion. So yes, we could either do it in 2 steps or we could do it in 1 step. So did people pick 2 steps, 1 step? We want to see it both. I have no idea where my example went. So 1 step, 2 step, any thoughts? You want to do it in 1 step? All right, let's do both. So I don't know where my 2-step example went in my notes, but let's try the 2-step conversion. So we said we can look at this, right? It's by the base. And so it's easiest if we'll go milligram to gram first, and then we can go gram to kilogram. And so let's set that up. So we'll do the first conversion factor. And so how do we go from milligrams to gram for our conversion factor? Excellent. So that looks good. So there's our first step. And then, okay, units cancel out. Excellent. And so now we're at grams. I'm not going to plug anything in yet. And so now that we're at grams, we need to go to kilograms. So what's our next conversion factor for that step? So 1 kilogram over 1,000 grams. So that looks good. So once again, our grams cancel. And so we could plug it into our calculator. So multiply everything across and divide it by everything underneath. So you could do 60 divided by 1,000 divided by 1,000. You could also realize this is 1 times 10 to the 6, so do 60 divided by 1 times 10 to the 6. Oh, my bad, I plugged that in wrong. So divided by 1 times 10 to the 6. So same answer. So 6 times 10 to the negative 5. kilograms. And then, so the one-step conversion, that's just involving if you can like directly see the conversion between milligrams and kilograms. So I'll just kind of write this out now. We'll do our kind of one-step conversion. And I really encourage the two-step because, again, that's kind of easier. We can reference our chart. But if you wanted to do it in one step, that's perfectly fine. So you just kind of have to recognize. So we have milligram. So that's 10 to the negative 3. Kilogram is 10 to the third. So that means there's a 10 to the 6th factor between them, right? So then we could write our new conversion factor. So our conversion factor, we can say 1 kilogram is equal then to 1 times 10 to the 6 milligrams. And then, so if we plug that in, we'll see that it gives us the same answer. And so now just formalities, so 60 milligrams. Putting my kilogram on top. 1 times 10 to the 6. And of course, plug that in. That's the same thing as that, so we get our same answer. So 6 times 10 to the negative 5th kilojoules. And so again, that's just your comfort level, whatever you want to do. If you can look at this and you easily see how to relate the two, just go for it. Otherwise, I would encourage you, just stick to one step at a time with your conversions, especially, we'll see that we use dimensional analysis when we start doing moles and everything. So you may have like every step, right? You'll convert to moles and grams and back and forth. So it's good to just kind of practice laying it out in a step-by-step fashion. Yeah.
6 times 10 to the negative 5th, would that be the same thing as 0.00006? And if so, would you take that answer?
Yeah, so, sorry.
It could be 4 zeros.
Yeah, that sounds right. 1, 2, 3, 4. So 1, 2, 3, 4, 5. Yep. And yeah, I would take that answer. So let's try this next one then. So meters to millimeters. And then, so what's my conversion factor? 1,000 millimeters over 1 meter. That looks excellent. So meters cancels. And then we get, what's our final answer? 2,500 millimeters. Excellent. All right. So let's try the next one. So 4.5 centimeters to kilometers. And so this one could have been one that you did a two-step if that wasn't obvious. And personally, I would probably do a two-step just to keep it clear. Any thoughts on this one?
1 over 100 and then again 1 over 1,000.
So you want to do 1 meter over 100?
Yeah.
So 1 meter is equal to 100 centimeters. So that looks good. So that brings us back to kind of, we'll call it our safe space, our base units. And then what did you say to go from?
And then 1 meter over, or no, wait, 1 kilometer over 1,000 meters.
1 kilometer over 1,000 meters. That looks good. And so now we just have to plug this in. We have 10 to the 5th on bottom, or we could do 4.5 divided by 100 divided by 1,000. So do we all get 4.5 times 10 to the negative 5? Any questions on that one? All right, let's go 77 meters to decimeters.
So 1 decimeter over 0.1 meters.
Over 0.1 meters. Sorry to think about that for a second. Yes, that sounds good. And then, so plug that into our calculator. So divided by 0.1. And then what do we get for our answer? 770 decimeters. And then you could have had like a different conversion factor here. In my notes, I just wrote 10 over 1, but this means the same thing. So. And last two practices. So now we have decimeter again to millimeter. And this might be another good two-step candidate. I would try going decimeters to meters to millimeters. That might be easier. Like, there's nothing wrong with what you said. It's just like in my brain. Then you have to figure out like the conversion factor of decimeters to centimeters first. And I'm just trying to work with like comparing to the base unit to keep it easier. So how can we go from decimeters to meters? So kind of multiply it by 10. So if you take this number by 10, so then it'd be how many decimeters? 10. So 10 decimeters. Does that make sense? So now we're at meters. So decimeters canceled. And then how do we go from meters to millimeters? 1,000 millimeters to 1 meter. So that looks good. So now meters cancels. So now I would multiply everything on top first. So I'll do 37 times 1,000 divided by 10. And that gives us a final answer of 3,700 millimeters for that one. And then the last one down here at the bottom, so centimeters to millimeters. And so this one, I would say either a 2-step or a 1-step is appropriate. So do we want to try to go direct, or maybe we should go to our base unit first? Would that be easier for us?
I think direct would be easiest.
There's just 1 in between, right?
Yeah, so then centimeter is 10 to the negative 2, millimeter is 10 to the negative 3. So then what's my conversion factor? What'd you say? 1/10. So 1/10 as in, yeah, so 1 centimeter is equal to 10 millimeters. So that looks good. So now we have our conversion factor, but then we have to plug it in. And so we'll switch that. So 10 millimeter goes on top, 1 centimeter goes on bottom, and then we get our answer of 0.02 centimeters. Oh, millimeters, my bad. That's what I get. All right, any questions on that one? So do we feel better about conversions today? Let's move on to kind of math and significant figures. And so this will be relevant, especially as you do today's lab. So I know morning people, you didn't have this advantage, but at least you can kind of go over things now. And so we said that the reporting of significant figures is an answer that is dependent on the precision of the measured values in a problem. So that means, right, if you went to lab this morning, you saw you can weigh stuff on the balance, right, it reports things to 3 after the decimal point, and you want to record every single number. Or when the ruler that you were using, it has little tenth marks for the centimeters. That means you can measure accurately to the tenth and then guess one more digit after. So that's where we're really seeing the physical connection between the instruments that we're using in lab versus the precision we're recording in our lab notebook and in these calculations. And then as we do it and you determine, how many sig figs you're working with, just know that conversion factors are always treated as exact values. So for instance, if you were converting between inches and centimeters, you wouldn't count this as 1 sig fig and then destroy all your sig figs. It's just a conversion, so it's just exact. Same thing with like a dozen, it's just 12 pieces equals a dozen. Don't need to worry about sig figs. And eventually we'll get to a mole is equal to 6.02 units. And again, not worried about sig figs. These are just our conversion factors. All right, so let's look at these sig fig rules, and then we'll go over how the math and everything works with them. So with our significant figures, so the first rule is pretty self-explanatory. So all non-zero values are significant. Does that make sense, right? If it's a number, it's important, we want to record it, and it's significant. And so this one, 536, 3 digits, 3 significant figures. Now the next one also makes sense. So if you have a 0 between non-zero digits, it's significant. And I also call this the captive 0 rule. So if you have a 0, right, it has numbers on each side, that means that that 0 has to be significant, right? It is accurately measured. And so in this case, 6,703, that's going to be 4 sig figs. And then these next 2 rules, so let's read them and then we can kind of summarize them. But we have first, it says, so leading zeros, so placeholder zeros to the left of a non-zero digit are not significant. And so it's saying, right, all these leading zeros, that's not significant. And so if you notice these zeros, they're just showing how small something is. And then if we compare that to our trailing 0 rule, so now it says zeros to the right after a non-zero digit are not significant. So if we look at this 7,000, all these 3 zeros are not significant. They're just showing how big. And so I just like to summarize these 2 rules as saying any zeros that show how big or small they're going to be not significant. And so the other way to think about this is if you can write it in scientific notation and just eliminate these zeros, then that's also telling you it's not significant. So for instance, right, if we write, so 7,000, that only has one sig fig. If we wanted to make that clear, we could do 7 times 10 to the third. That's still one sig fig. But let's say you had an instance where, well, you know, this 0 is accurately measured. I know that this is a 0. We could also use scientific notation to help us. So then we could write 7.0 times 10 to the third. Same number, but now we're saying, okay, now we have 2 sig figs. And so you could keep going with this. So now we have 7.00, again showing we measured accurately to the 10th place. So times 10 to the third, 3 sig figs. And let's say you wanted to show that all these numbers were significant. We measured 7,000 accurately, precisely. We know that. Then write 7.000 times 10 to the third, 4 sig figs. So you kind of get the point there. And then we have this last rule. So zeros to the right after a decimal point are significant. And so this is saying, I call them unnecessary zeros, right? If you're bothering to add these zeros to the end, then you're showing, yes, we measured accurately out to the 10th place, out to, right, the thousandth or the millionth place. So, and so in this example, so if we look at 0.0600, right, this 0 is not significant because it's showing how small, but then these 3 are. So now we have 3 sig figs. And then, so when you're measuring your glassware and everything, so we have our instruments. We want to determine the last digit by estimating between the mark. And so you're going to have to evaluate, right, every piece of glassware that you're using because they could have different marks, even with these 10th places. So if you look, this is marked every 0.1. I've seen glassware that's sometimes marked every 0.2. So you just have to kind of watch it there. And then so for this one, and let's zoom in just a hair so we can see. And so if we're looking at a graduated cylinder, so we're assuming this is milliliters, so this is every 0.0 milliliter. And then so what can we write our guess as to what the volume is? So if we're looking, so 4.6, because we want to add another digit, right? Because we can report, and if we're looking at it, because this is 4.5, and this is 0.6. So to me, and you may think differently, I think it's a little under the 6. But if you thought it was exactly at 6, then you would want to write 4.6. But then we have to report it to another digit after saying like, oh, I precisely think it's on there. So this is our uncertain digit. Now, me looking at it, I think it's kind of in the middle-ish between the 0.5 and the 0.6. So I would write like 4.56 maybe, 4.55. Again, you can have different numbers here just based on how you measured it. But then this also gives us, right, our 3 sig figs, which is important. So we don't want to, another way you can hurt like your lab result is not giving yourself enough sig figs. So you want to make sure you're reporting enough so then when you start doing the calculations and lose numbers that your accuracy isn't completely lost. So always guess that extra digit. And then, so let's look at these. I'll give everyone a minute or two to kind of think about what their answer is, and then we'll go over with just showing fingers how many sig figs we think they are. So let's look at number 1 here. So 54,000, so show me some fingers. How many sig figs? Let's see, excellent. I see 2s everywhere, so good job. So these zeros, right, they're just showing how big, so they're not significant. What about number 2 now? Let me see some fingers. So 3s, 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 excellent. So 3 sig figs. Number 3. I see some wild fingers. So remember, all these leading zeros are just showing how small, so excellent job. If you had 3 fingers up, and I'm glad you caught that extra 0 at the end too. If you got 3, so that 0 was significant. And then 4,500,000. See 2s. Good job. And then let's see if anyone fell for the trap in 5. How many sig figs? So different answers all around. So this is a tricky one. So I saw some 2s, and so 2 is what it's supposed to be. But this is kind of ambiguous, but textbooks still use it. So if they put a decimal point after it, this now means that these numbers are significant. However, you know, I like to say, if you have a random period there, I feel like that's when you grab your magnifying glass out and you're like, is it really there? Is it significant? And so to make it clear, it would be better to write it 1.0 times 10 to the 1 to really show, okay, I clearly have 2 sig figs that I care about. But excellent job, even with that tricky one. All right, so then this will be really relevant not only for today's lab, but every other lab kind of going forward. And so this is the quick summary, and then we'll do a review. And so with multiplication and division, I think they're the easier ones to handle. And so with multiplication and division, it is the least precise measured value that determines the number of sig figs in the reported answer. So, you know, you look at your 2 numbers, see which one has the least sig figs, do the math, and then you report to the one with the least number. With addition and subtraction, I always say you kind of have to set it up almost like elementary school style so you can see. And what you want to look at with addition and subtraction is that the value with the smallest decimal measurement determines the answer's significant figure. So basically what it's saying, you can only report after the decimal place to the one that's the smallest after the decimal place. So if you have a number that only goes out to the 10th place, so you know 10.1, you can only report to that point, 10, you know, whatever it would be from your addition and subtraction. So let's look at some examples so that we're all clear on that. And so if we look, and I'll plug it into my calculator so we can all follow along. So if you were to do 3.56 times 4, all right, so that spits out 14.24. But then how many sig figs do we have here? So how many sig figs do we have in 3.56? And then how many do we have in the 4? So 1. And so this is what limits us, is 1. So we can only report to 1 sig fig now. So that means we have to take this 14 and we'll round it down to 10. So you can see we really lost some numbers there. So again, that's why in lab you want to make sure you're reporting all the digits that you possibly can. And then for this one, so now let's plug this in. So 2.050 times 5.0. And then, so what's our number with our fewest amount of sig figs? What would that be? So excellent, so we only have 2. So we can only report this to 2. And so that means, right, our answer is going to be 10. But we have that awkward scenario where we need to indicate that that 0 is indeed significant. So you could either write the answer like that, or like it says here, write it in scientific notation to get rid of that ambiguity. I don't know why I put 2 in a second. Okay. And then so division, same thing, so same rules apply. So 45.0 divided by 9 spits out this answer, but we only have 1 sig fig, so we can only write 5 centimeters. And then, so looking at this one, so notice, right, this is a conversion factor, this is a conversion factor, this is a conversion factor. So none of those count towards our sig figs, so we only care about the value we started with. So we started with 2 sig figs, so we need to round this to 2 sig figs, so that's a 7, so that gives us 1.4 there for that answer. So hopefully that helps you with lab. And then so let's look at addition and subtraction. So in this example here, so we have 23.467 plus 313.21. And so notice our limiting one is going to be this 313.21, since it's only reported 2 after the decimal places. So that means we have to report our final answer to just 2 after, and so that's why they rounded it to 336.68 there. So same thing for subtraction. So again, this can get you some funny scenarios sometimes. So we have 457 minus 0.68, but we had no accuracy here, right? We don't have anything after the decimal point. So unfortunately, we can only report to our whole number, so we would write 456 centimeters. So does that make sense with the addition and subtraction rules? So just keep, like I said, do your addition and subtraction kind of in this style to help you. Then you can really see, or just keep track of who has the least amount of decimal points. And hopefully the multiplication and division was at least simple enough to follow. And then just always be careful in lab, since every step you'll have sig figs and need to calculate and deal with them appropriately. And then, so scientific notation, this is just kind of a recap, so we're all on the same page, and that we know how to handle scientific notation. So again, looking at these positive exponents, that means we have a large number, so move it over to the right 4 times, so 1, 2, 3, 4, that gives us our number. So same with this 24,327, we can also write it in scientific notation. And all scientific notation means is you have some number of x, then a decimal point, then whatever other numbers, and then times 10 to whatever factor. It's a lot of variables. And so same thing, if you have questions, again, please just stop me. I'm not trying to go over anything that people know too much in detail, just trying to give a quick refresher. And then, of course, we see right with our negative exponents, so if it's negative, it means it's a small number, so we start with 1, move it over 2, so 1, 2. This number, negative 2, so 1, 2, so 0.053, that's the same, and all that kind of follows. Any questions on scientific notation or anything? Feel okay about that? All right, so let's switch over to now our temperature scales. So temperature is important. I think we brought it up in this class that usually we use Celsius, and then sometimes we have Kelvin. And so let's look at our temperature scales for comparison. So we have our big water freezes, so that's kind of a good marker to orient ourselves. So you probably know water freezes at 32 degrees Fahrenheit. What's nice about the Celsius scale is they wanted to make easy numbers. So they set water freezing at 0 degrees Celsius, and then water boils at 100 degrees Celsius, and of course compared to 212 degrees Fahrenheit for water. And then, does anybody know what the Kelvin scale is based off of? So it gives a hint of absolute zero. Have you ever heard of absolute zero before? Do we know what that is? Yeah, so that's it. So it's the lowest temperature, but it's really a theoretical measurement. And so really what defines absolute zero, it's the absence of molecular motion. And so we're learning, or we're going to be learning, right, that electrons are always moving around, so they never stop going. Right, they're always circling around the atom, but at absolute zero, there would be no molecular motion. And so again, we'll learn, right, atoms are always vibrating, moving, but at absolute zero, motion ceases to occur. And like she said, right, that is the lowest possible theoretical temperature. So of course, once you stop all molecular motion, right, you can't really get any colder than that. And so, like I said, absolute zero is kind of a theoretical thing. They've gotten pretty close. I'd have to see where they are. I remember a couple of years ago they had gotten to like 4 Kelvin or so, but I know they've probably gotten a little closer. I would just have to look at the research, and they come up with all these intricate setups to try to thermally isolate everything. It's pretty crazy research. But anyway, so that's what Kelvin is based off of. And so if you look, 0 Kelvin is obviously the absolute zero. But then what's kind of nice is we can easily convert between Celsius and Kelvin. And so our temperature Celsius, and you can see it with our water freezes, all you do is you add 273 to whatever Celsius temperature you have. And that equals your temperature in Kelvin. And it's technically 273.15. I'm just putting that on there so you know. But honestly, I never, I don't think it'll come up where you would need that accuracy unless you have like a specific problem that says like, what is the temperature Kelvin if it's exactly like 0.00 degrees Celsius. But you'll see with our thermometers, they're not that accurate where that 0.15 really matters. So when you see me doing the conversion in class, I generally leave that off. And so then we also have our formulas for converting. And so I wouldn't expect you to memorize these formulas. They're usually provided, but you could also write them down on your cheat sheet. You just need to know, how do I plug that in? And so we have our Fahrenheit conversion. So if you have your temperature Celsius, you multiply it by 9 over first, then add 32 to get your temperature in Fahrenheit. And you might also see, so if we look, right, 9 over 5 is also equal to 1.8. So if you see a formula in the textbook like 1.8 times the degrees Celsius, just don't let that confuse you, right? It's the same thing. And then if you want to go from Fahrenheit to Celsius, so notice you have to subtract first. So you take your temperature in Fahrenheit, do the subtraction, then you can multiply it by that 5/9 factor. And again, so what's 5 divided by 9? So if you see like 0.55 or something in another textbook or resource, again, no, that's where that came from. Right. Let's hit up density, and then we'll be ready to do practice problems. So density is just defined as a ratio of mass to volume, and I also like writing it in this form. So you put whatever variable is on top, like if you have some equation in this form, so mass goes on top. Density, volume. Have you guys seen this triangle trick thing before? I think somebody has, but. So the triangle trick, I like setting it up like this. Even though we can use our dimensional analysis and algebra and everything to figure out what to do, sometimes it's nice to have a sanity check. So for instance, let's say you wanted to solve for the mass and you had density and volume. What you do is just cover whatever variable you're looking for. So I cover up mass, and then it tells you what to do. So density and volume are right next to each other, so all you do is multiply them together. That gives you mass. If you want to find volume, cover volume. That gives you mass over density, and that's what you do. And so same thing, right, density. That's kind of obvious, though, since that was set up originally. But same thing, cover density. Mass divided by volume gives you density. So let's try this first example. So let's do this first one. We'll do it all together. So it says, if a 73.2 milliliter of a liquid, so this is our volume, has a mass of 61.5 grams, what is its density in grams per milliliter? And notice the density, so it's going to have some funky units, right? So it's going to be some sort of mass over some volume for the unit. So this is a common one that you'll see. You could also see though like kilograms per liter or some other combination of kilograms and liters and volume. But then for this one, so we have our formula, density equals mass over volume. So we're given mass, so 61.5 grams. We were given volume, 73.2 milliliters. And so now we have to just plug that into our calculator. And so does everyone get 0.840 or something? And then so now we have to take our sig fig rules. So we have 3 sig figs from our milliliters, 3 sig figs from our grams. So either way we need to report to 3, so it should be 0.840. And then again, our units are going to be gram per milliliter on that density. So see if you can try this next one. You at least have answer choices to help you. So don't forget the triangle trick. I can rewrite the triangle, but see if you can determine the volume then of an object that has a mass of 455.6 grams and a density of 19.3 grams per centimeter. So did we figure out what numbers we need to divide by, or? Let's see.
Mass divided by density.
So
455.6 divided by 19.3.
and then, so notice, so if I set it up this way, so divided by 19.3, and so this should also work out with dimensional analysis. So I don't know if you used the triangle trick or you just figured it out or what you used. So you could, right, cover that, see that it's mass divided by density. But then our units will also match. So notice how grams cancel. We're going to be getting centimeters cubed, which makes sense. That's a unit of volume. And so just so you know, centimeter cubed is also equal to 1 milliliter. And so now let's plug this in, or you could tell me A, B, C, D, E while I punch this in, what you guys got. So D, excellent. I heard a lot of D's, and that's what I got there. So good job on that one. Any questions on this example or density problem so far? And then, so just a term that I wanted to bring up, since it comes up in your book. So it talks about this term of specific gravity. So all specific gravity is it's just a ratio. And so usually, more generally, it's just a ratio of the density of two substances. But then your book kind of has a slightly narrow definition where it's just the density of some substance compared to water. I want to say more narrowly. But then, does anyone know offhand what the density of water is? Yeah. One, I like the zero guess, but one is a correct answer. So water is one of those substances we compare kind of everything to, since water is one, so then you always see, like, does it sink, does it float? And so really, you would just take the density of your substance divided by the density of water, but it kind of equals the same density. So for example, let's actually look at the density. So the density of hexane, so hexane is just a six-membered carbon chain. So it has a density of 0.66 grams per centimeter cubed. And so we know, right, the density of water then would be 1 gram per centimeter cubed. So if you divide them, you notice that the units would just cancel out. It's 1, so it doesn't even really matter. So we would just get a specific gravity of 0.66. So again, this probably won't come up too much, but I at least want to mention it because it is in your book. Just more of a formality. All right, let's do a bit more practice then. So try this one on your own. So we have, what is the mass of 6 cubic centimeters of mercury if it has a density of 13.5939 grams per centimeter cubed? So I'll give everyone a minute or so to work on it, and then we'll go over it. No, sorry. we get an answer yet? So let's see, we're trying to find mass. So what do we need to do?
Density times volume.
So density times volume, I like it. So you could cover up mass, right? Reminds you what to do. Or if we look at our dimensional analysis, so we take our density, so 13.5939 grams over centimeter cubed, multiply it times our volume, so 6.00 centimeters cubed. So notice centimeters cubed cancels out, so that just is going to leave you with a mass. And so let's plug that in. And please make sure I don't plug anything in wrong. And so do we all get 81.56 something? And then how many sig figs should we have in our answer? I like the 3. So remember we started with here. So we have 3 sig figs from our mass, and that one has 6, so a lot. We'll report to our fewest, so 81 point, and then what do we round it to? Excellent, 81.6 grams.
Is there 3 sig figs because there's the decimal with the 2 oh.
Yeah, since they bothered to write 2 zeros after the decimal point, that's telling us that they measured it that accurately. So see if you can try this one. Although, let's pull up. Let's go back to the formula. So we need to convert from Celsius into Fahrenheit. And so let's take note of the formula, if I can find it again. So Celsius from Fahrenheit, so Celsius is equal to 5/9, Fahrenheit minus 32. Oh, we want to go the other way though, my bad. Or so Fahrenheit equals 9/5 degrees Celsius plus 32. All right, did we get an answer for degrees Fahrenheit? Let's hear what we got. So times 9/5 plus 32. So what do we get for an answer? So 5,000.
5,371?
I like it, 5,371. And good job with the 4 sig figs there. And then, no, I don't know what I wrote. So that was degrees Fahrenheit. And then what about Kelvin? So how do we go from Celsius to Kelvin? Oops. So 299, or 2966 plus 273 to get us to Kelvin. So do we get 3,239 Kelvin? All right. So that's all I have kind of formally prepped, although I did want to take a look at the homework. So I don't have the homework on the computer. But I wanted to point out what I was talking about with the whole exactly thing. So if you look, for example, at your temperature scales homework, and then number 2, and what we can do this together. And so it says there, convert the freezing point of water, and it says 0 Celsius exactly, into Kelvin. And so anytime it says exactly, that would be the only time where I would include that 0.15 factor. And so if we want to convert, right, so then that would be 0.00 basically degrees Celsius. We want to add 273, except now I'm going to bother adding that 0.15 since it said exactly. So then our answer should be 273.15 Kelvin for number 2. And then so same thing, so if you skip down to number 4 then, it has that same wordage where convert absolute 0, so 0 Kelvin exactly into Celsius. And so Kelvin, also notice with Kelvin, Kelvin doesn't have a degree symbol. So just note that when you're writing this. And so again, we'd want to use that factor. So we have temperature Celsius equals, or excuse me, temperature Kelvin equals temperature Celsius plus 273. So now we want to subtract, and I should have added that 273.15. So now we'll do 0 Kelvin minus 273.15. So that means the absolute 0 temperature in Celsius is, of course, negative 273.15 degrees Celsius. And again, that's only because it says exact. As that is not a normal scenario. Any other questions or anything so far for this chapter? Let's do one more practice and then I'll let you go a few minutes early. Where did my example go? So let's just do a conversion of length. And so the whole point in getting comfortable with the conversion factors and the metric conversion factors is then we can just apply it to anything. And so let's do another example. So convert 60 inches to centimeters, and given that 2.54 centimeters equals 1 inch. And let's do 60.0, or just so we don't lose too many sig figs. Sorry about that. I'll rewrite that. Do we get an answer for this? Punching it out. I'll start setting it up. But essentially, right, you could be given any sort of conversion. So on an exam, I could do like blips to blops and give you random numbers. So just be prepared. The key thing is, can you get our units to cancel out? So if we want centimeters, we'll do 2.54 centimeters on top, or 1 inch on bottom. So now you can see inches will cancel. We'll get centimeters. And so what do people get for their answer? So 152, and that sounds correct since we only had 3 sig figs. That looks good on the rounding there. Yeah.
If we didn't have, if it wasn't at 60.0 and it's just 60, would the answer have to be 150?
Yep. So yeah, good questions. Other questions? All right, I will let you go then. And so please write down whatever the muddiest point was or whatever you still have confusion over. If you didn't get one, I still have yellow sheet. And then just put them here and put your name on it too. It'll just be a small participation, or we'll see how I count them. I don't want to count anything against you, but being present in class, that always tells me you're trying, you're doing well, and I can always look favorably on your grades when it comes down to it. So thank you again, and I'll see some of you really shortly at 2:30. And so if you didn't come to lab this morning, I expect you in lab today.
Yeah, so I don't know if you remember I came yesterday, but I got my schedule fixed, so I didn't get the homework from yesterday.
Oh, okay.
Would it be possible to get that today?
Yeah, I was trying to see if I have any on me.
Or I could just take a picture of it and, just,
Actually, I think I have. Yeah, this is an original copy. I don't have a copy, but I don't need the original. It's just not stapled.
Okay,
But if
sounds
that's
good. Yeah,
okay.
I came in
All right,
like 2
thank you.
minutes early. 2 minutes late. Can I get a paper
Oh.
to sign? Thank you.
Yeah, so just put your name on it, and if you had any muddiest point or what needs clarification.
Okay.